In this problem, we are supposed to compute the voltage drop along a 21-meter length of household number 14 copper wire. The wire has a diameter of 1.628 millimeters and carries a 12 amp current. So as soon as we start dealing with, some amperage and a voltage drop and a length of wire and a thickness, there are several concepts that we probably are going to need. The concepts involved here, we've probably are going to have to use Ohm's law. Ohm's law relates the drop in voltage across a wire with some current running through it and some resistance. Now, because they are not giving us resistance directly, but they are telling us about length and thickness, we are probably going to have to think about not only resistance, but we are going to have to think about resistivity. Okay. So before we write down some equations, let's go ahead and draw a picture. Typically, wires are sort of cylindrical in shape. So let's look at a kind of cross-section of what one of these lengths of wire might look like. Circular cross-section with a particular area of that cross-section, and it might be related to pi r squared, where r would be the radius of that cross-section. Now this thing has a particular length, L, and usually what is going on is there's some current that's flowing through it, so I might draw that with a little arrow and indicate there's electric current going in that direction, say. And in addition, there's a relationship between this current and the applied voltage. The applied voltage would be something like this. If there was a voltage here that we could call V2 and a electric potential right there called V2, and let's call the electric potential V1. They are not the same. Current likes to flow from high potential to low potential. So there is a change in potential. There's a so-called voltage, which is the high voltage minus the low voltage. Okay. So there are a couple of things that we've identified. We do have a voltage that's related to the voltage V2 and V1, but we don't necessarily need V1 and V2 separately. What we do have are Ohm's law. So Ohm's law relates this voltage to the current flowing through the wire to the resistance of the wire. And we don't know the resistance of this wire, but we do know a relationship between resistance and resistivity. Resistivity is given the symbol rho, the capital letter rho, whereas resistance is capital R. The resistance is proportional to the resistivity. Resistivity is an intrinsic property of some material like copper, and it grows proportionally to the length of that piece of copper, and it's inversely proportional to the cross-sectional area. And so that's how resistivity comes into this. Okay. So since we are looking for the voltage drop along this piece of wire, we can combine these two equations. Delta V, write this as delta V equal to the current, which is given, times the resistance, which would be given by resistivity, times length divided by the area. And so we need to figure out what all of those numbers are. Maybe off to the side, what I could do is figure out what is the area. This is the area of pi times the radius of the piece of wire. The radius is the half of the diameter, so 1.628 millimeters, or 1.628 times 10 to the minus 3 meters diameter. Divide that by 2, and don't forget that that needs to be squared. We can work this and get the area to be 2.081, and I'll just keep some extra digits around for now, times 10 to the minus 6 meters squared. So that's a number that we'll use. We also need to know what is the resistivity of copper, and so the resistivity will be the resistivity of copper. Looking that up in a standard textbook, what you'll find is this is 1.68 times 10 to the minus 8 ohm meters, ohms times meters. And this is assuming that the temperature of the copper is not radically different than the temperature at which this value is measured. So this is roughly room temperature. Let's just make that assumption here. So now we have all the values we need, and we can start plugging things in. The current, we're told, is 12 amps. The resistivity 1.68 times 10 to the minus 8 ohms times meters. The length of 21 meters, and then the area goes underneath all of that, 2.0816 times 10 to the minus 6 meters squared. We can work this out with a calculator, but let's check that these units actually do what they're supposed to do. We have on top meters times meters, so there's meters squared on the top and meters squared on the bottom, so those do cancel, and we are therefore left with amps and ohms. The number we get here is 2.03 amps times ohms. We are limited to an answer with 2 sig figs, and so I'll write this as 2.0 amps times ohms. That has the same units as volts, which must be the case if you look here at Ohm's law. 2.0 volts for our final answer.